Okay, so I started you off with one that I was like, oh, that's pretty easy. I didn't really think about it, and then when we were at the office hours today, I was like, oh my gosh, this one is actually really, really tricky. So with this one, what we're looking at is two circular wire loops represented above our, or I guess below our coaxial, so it just means that they're laying in the same plane. If the current I in loop A is increasing linearly with respect to time, which of the following is true of the induced current in loop B? So what we're looking at is this situation where we're increasing our current. So let me get a different color. Our change in current with respect to time is equal to a constant, right? They say that it's kind of this linear. So if we were going to graph that out, if we we're going to graph I versus t, and we graphed it out, it says it's linear. So we'd have this y equals mx plus b relationship, where we say I equals some constant, whatever, m times t. So really what we have is this idea that our change in current over our change in time is a constant value. So we'll get back to that really quickly. But first I want to talk about what direction we're looking at. So over here I kind of drew this out. I think it's easier to think about it in this sense. So we can use our right-hand rule to figure out that we have this current that's going in this direction, and if we kind of trace that through, outside of our loop we see everywhere our current is to the left, inside of our loop everywhere our current is towards the right. So we know that current around a loop is kind of making this circular distribution. So this is what we have inside of this loop. So we're slowly increasing the current, which means, let me come down here really quick. We have this equation, this B, this magnetic field is equal to mu naught I over 2 pi r. We said this is our magnetic field equation for a current of wire. It is slowly increasing, or sorry, we see that this I is slowly increasing, which means that our B is also going to slowly be increasing at this linear rate. So I is increasing, which means that our field is slowly getting stronger, which means our field starts to affect this other loop. We start to get a magnetic field in this loop that is going to the right. So within here, based on, see this picture, we have these are going to the right. We have magnetic field within this loop that's starting to go to the right. And we know with flux, nature does not like that. It doesn't like that change. So it's going to the right, and it's saying, hey, I really liked not having any magnetic field going through me, so I'm going to create a magnetic field. I'm going to induce a current, so I can create a magnetic field that is going to the left to counteract this rightwards magnetic field. So then if we do our right-hand rule, we see, okay, if we want our fingers to wrap in that direction, then our current has to be going in the opposite direction. So we definitely know that our answer has our current going the opposite direction to induce that oppositely facing magnetic field. So we know it has to be the opposite, then we just have to think, is it going to be constant or is it going to be increasing with time? And that's where it starts to get tricky. So I'm going to step through this and hopefully it kind of makes sense. But so what we have is this idea that we have this equation, this is kind of like looking at the first loop now. So in this loop 1, we're saying that we have this constant increase in current. So our change in current over time is this constant value, which is then changing our magnetic field over time. So as we increase our current by some amount, our magnetic field is going to increase by some also linear amount. So our change in magnetic field, where you can really think about it as we have this change in magnetic field over time is equal to our change in current over time. So this is kind of weird, but I just kind of made it a rate. I put the current over the time is equal to our change in magnetic field over time. Because throughout this, we're not changing R, we're not changing mu naught, we're not changing 2 pi. So we can really say, hey, our magnetic field is increasing throughout time based on this linear increase in current. And then now we're going to jump over to loop 2. We're saying loop 2 is starting to get this flux going through it. It's starting to get this magnetic field going through its area. And then we know that it's starting to get that magnetic field, and we said that this magnetic field, this changing flux, is going to induce a voltage, an EMF. And we know that V equals I times R. So if we change our magnetic flux over time, we induce some sort of current I. And that's what we want to look at. We want to see, oh, is this I increasing or is it constant? So we are changing up, if we kind of look over this, if we replace our flux with the actual B times A equals I times R, what we can say is, oh, well, area is not changing, so area is kind of a constant. Let me highlight the constants. So area is constant, our resistance is constant. So we can look at it and say, oh, well, if this B, this change in magnetic field over time, if that's a constant value, then I know that my I is going to be constant, right? Because if something's changing on this side, it has to change the same amount on our right side of our equation. So let's go back over to what we saw initially. So over here, we said, oh, well, our change in B over our change in T, that was going to be equal to mu naught I over T over 2 pi R. On this side, well, we said that this change in current over time, it's linear, it's a constant change. Where do we draw that? We said this change in I over change in T is just equal to a constant because it has this linear relationship. So that's a constant, which means that this side throughout time is going to be a constant. So if this B over T is constant, this I also has to be constant. So it feels weird that it's not changing, but it's really because our flux is changing at this constant rate. That means that our current has to be constant. So our answer is actually this opposite with a constant current with respect to time. Then for this next one, they get a little bit more straightforward. A circular conducting loop is in a region of magnetic field B directed out of the page as shown above. The magnitude of the magnetic field is decreasing. The direction of the induced current in the loop is going to be counterclockwise because we have this magnetic field that's out of the page, but that magnetic field is slowly decreasing. So because it's decreasing, the current or the loop of wire is like, hey, I don't like that we have this flux. I don't like that we have this change in magnetic field without this area. So because of that, I'm going to induce a current. I'm going to have this EMF that will create a current. And it's going to do it to replace what it's missing out. It doesn't like that change. So it's like, hey, I want as much magnetic field as before. So it's going to create a counterclockwise current. So based on that right-hand rule, that we will create a magnetic field or induce a magnetic field that is inside of the loop so that we are counteracting the decrease inside the loop. So it's saying, hey, I liked how much I had before. I'm going to induce a current so I can have what I had before. So we're going to have to be counterclockwise to make that happen. And for this final one, it's very similar to what we had on the free response question. So I'll go through it really quickly, but kind of for a more in-depth explanation, I would look at the free response question. But so what we're saying here is the gray rectangle in the figure above represents a region of uniform magnetic field directed out of the page. A square loop of wire of side S is in the plane of the page and is pulled at a constant speed V through the field. Which of the following could show the current I in the loop as a function of the position of the right edge of the loop? So what we can say is this loop, it has some sort of height y, and has some sort of distance s. And right now we don't care about really the loop, we don't care about the area of the loop, because when we're looking at this area, we care about the area that is inside of the magnetic field. So instead of, this is kind of going to gradually change. So instead of calling this full distance s, let's look at this piece of our distance. Let's call this some position x. So we can say the area inside the loop is equal to y times x. And then what we also know is this thing is moving at a constant speed. So once we get in here, the amount of area that's going to be within our magnetic field is changing as x changes. And we're saying because we have a constant velocity, as the problem told us, our change in x over our change in time is going to be equal to v, and it's going to be a constant increase. So if we look at this, we can really say, oh, our area, the way that our area is changing over time, our area is x times y, that's changing over time. So our area over time is really equal to y, which is not changing, times v. And then if we look at this equation for magnetic flux changing over time, And we want to do that because we know that this is going to induce a current, and we care about the current over time. So we really have this over time is equal to I times R. In this case, the magnetic flux is equal to B times A times R, and we said this area over time is really equal to Y times V. So B, Y, V over, I don't have time, equals I times R. And in this case, what feels really weird is it feels like it should be changing, but we see, oh, okay, in this case where our magnetic field, where the area is changing, the area within the magnetic field is changing, B is a constant, Y is a constant, V is a constant, R is a constant, which means that I has to be constant. So within here, in this little initial step, some of this. So in this initial step, where we are changing the amount of magnetic field within that loop, so in this first little piece, this first up until S, we're changing the amount of magnetic field within that area. Then in this middle piece, we are filled up. We have a maximum amount of magnetic field in that area. And then here, when we're pulling it out, it was like, hey, I kind of got used to having this magnetic field out of it. Now I'm going to induce a current in the opposite direction so that I can kind of relive those glory days and have that magnetic field out of the page again. So we go from it being like, okay, I need to induce a magnetic field into the page to counteract this new out of the page one. Now I have this constant, or I have this zero current because it's not changing the flux. And over here it's saying, oh, now I have to do the opposite because I want to have it out of the page now. I liked what I got used to. So we need to find a thing that has a constant current, 0, and then a constant but then opposite current, and that is going to be C. Alright, so that is that one. Hopefully that was okay.